11-1. We're going to skip field between two charged plates temporarily. We'll come back to it. Don't cross it out, but we're going to come back to it. Faraday's next idea was even more interesting because it actually saved our bacon. It's a term we use today, although his name isn't on it, which makes sense because why would you put his name on it? He invented it. So you have this field of charges in a piece of plastic or whatever, and I bring a charge next to it. And let's say I want to move it to here. How much work would it take? Tell me how you'd approach this problem. Work equals force times distance. So you'd have to do what?
Can we find the total force of like the block though?
Can you?
Yeah.
It's even reasonable to assume you can.
Yes. Because we just talked about
It gets worse than that because as I move it, what's going to happen to the force, Blaze?
It's going to change.
It's going to change, which means I've got to integrate what I just drew. Now this poor glue sniffing person said, "Oh no way, not gonna do that. Not even no, not." So I came up with an idea. And the idea is parallel. So we'll explain this. I'm going to try to do something similar to it that's not the same. Let's say I've decided, me and Blaze, we decided we're going to make a different kind of music than anybody's ever heard before. What we're going to do is we're going to take a big old metal plate and we're going to lay it on the ground right at the bottom of the cliff. And we're going to climb up to the top of the cliff and we're going to stack a set of rocks up there. And we are going to drop rocks down a 100-meter tall cliff. And so when they hit the panel, we can hear it ring. Yeah? He's in. Now we could vary the tone of the note by hitting different sides of the plates with very careful aim. How do we vary volume? Loudness, Blaze.
Throw it down.
Good, but that'd be a little bit shaky, right? Because then I'd have to throw it exactly right. So let's not vary that. What else could I do? Raise the cliff? Not doing that either because I'm lazy. What else could I do?
You could bring a ladder to the top of the cliff.
Yeah, you raised the height.
Or I could choose different sized rocks, right? I could take a whole set of rocks up there. I could take little rocks, big rocks. Then I wanted to vary the volume. I could drop the rocks around. That's a little easier than changing the height of the cliff or throwing it carefully downwards. But your suggestions work. So, but I'm going to talk about dropping rocks. Now, here's an interesting thing. How would I calculate how much energy a rock would deliver? Blaze, what do you got for me?
However much energy it has.
So how would I figure how much energy I have per rock? MGH. Now what's interesting about this is after a while we'd get pretty lazy because we don't want to sit there and make the calculation between sounds. We have to get this right? So we're dropping rocks over the side and they're each hitting, making it slightly apart. We've got the time figured out because we know how much time it takes to go to the bottom. We know what to put the gaps. 1 second later, it's going to make a sound 1 second later. We got all that figured out. We want to simplify this formula. We know G and H don't change, do we? So we're going to make that 9.8. We're going to make this 100, and we'd have 980 times M. Agreed?
Yeah.
That would be my potential energy formula. And so all I do is say, okay, I want a 980 sound, 1 kilogram rock. We'd probably be lazy to make it 1,000, and we just drop the rocks. 2,000. I want a half. Okay, half. 500. Right?
Yeah.
And we can vary the noise that way. Point A, point B. Here's what I'm going to do. The only thing that mattered in my experiment was the mass of the rock, right? So I'm going to pick 2 points in space, and I'm going to take my 1 Coulomb charge, and I'm going to drag it over from one spot to the other spot. I'm going to figure how much work it takes. Great. Work's energy, right? I'm not going to actually calculate directly. I'm just going to pull it and figure out what I'm check my spring scale again. See what the force on this spring scale says, and I'm going to pull it that distance, and I might have to do one integral. But I would get the energy it takes to move 1 Coulomb charge from A to B. Great? Okay. Then, how much energy would it take to move a 2 Coulomb charge? Mrs. Swick? Why so much? 3 would be 3 times as much. 4 would be 4 times as much. 980 times whatever mass is. 1 would be 980. 2 would be 2 times 980, right? So once I measure this, just tell me the charge and I'll tell you how much work it takes. Okay? So the energy, which would now be U, is going to be equal to the charge I drag across it times I need another letter. I need another thing. Now, logically, we put an F right here because that is probably Faraday's greatest accomplishment, but we don't because he didn't measure what, he never actually thought this was a real thing. He just used it for math problems and solving these really funky things. Along came another guy who actually measured this quality. His name was Volta. And so we, for a long time, called it voltage. It is no longer called that because physicists are dumb. They're going to call this electro, wait a second, motive force, which is measured in volts. Now, you know volts. You've seen volts. Where you seen volts, Karis?
I'm half tempted to say right there as reference to Ursula, but circuits last year.
Circuits last year, even simpler than that. You've been dealing with voltage your whole, batteries, right? Yeah, a 9-volt battery, a 6-volt battery, right? That's how the battery is simply designed. So if you have a 9-volt battery, what that means is per every 1 Coulomb you throw from one to the other side, you create, if it's a 9-volt battery, 1 times 9, I'm going to do how much energy? 9 joules, done.
Wow.
That's, imagine if you went to the store with this problem, right? I need a piece of copper with a bunch of electrons on it spread with a density of about this much, and I'm going to attach it to another piece of copper where it's electron less dense, and this is about what, and by the way, when they start to move, it's going to change my answer, so I'm just want to, and by the way, if I use twice as much charge, I'm going to have to redo my calculate. No, you don't. Done. Use this today. Okay? So voltage is everything about energy except for the charge you're delivering. It's essentially like how high the cliff is, what planet you're on, so you know when you drop a rock how much energy it's going to deliver when it gets there. Battery says it's 9 volts from here to here. You tell me the charge and I'll tell you how much energy you gave the Laughing Kathy doll. Right? That's why you don't put bigger batteries in things unless you're like seeing them melt. Because they'll deliver more energy per Coulomb than you meant to. Which what happens to your Laughing Kathy doll? You have exactly the amount of energy you need to make her laugh, and then a little bit extra to make her melt. Because where's that energy going? Heat and sound. Not going to make much sound. You'll hear the sound, you hear the zapping, but you'll also hear it. You kind of start to smell the plastic melting. Okay? That's why you don't do that. Blaze, why did it sound like it gave you an idea rather than helped you out? Does this make sense?
Because that's exactly what you did.
No.
No.
All right. Don't melt
Yeah,
things with
look up a
electricity.
car battery.
It's a bad habit to get into. All right. Now I'm gonna. So this is the voltage thing. Now parallel plates are fascinating. So you did so far?
That's the voltage formula?
That's the voltage formula. The voltage formula is this right here. Actually, I'm usually going to write it as VQ. I apologize. I wrote it backwards, but
It's okay.
for our purposes, that makes sense.
Look out.
Okay? Now, there is something strange about parallel plates. At this point, I usually get out my parallel plates, but doesn't mean anything because you can't see it. What's weird about them anyways, but you know, it's fun. What are parallel plates? There are two metal plates. Metal, metal. Yes. It's the beginning of the worst experiment ever. Yes. Two metal plates. Okay? You charge them so that this charge is the same as this charge.
It's the same, but opposite.
Same charge, but opposite. Turns out if you make them the same, it's a whole different problem, but it works the same way. If I put a particle in here that's charged, the electric field at this spot is going to be the same as the electric field at this spot. Does that make sense? What's weirder is, as I move away from this plate and close to this plate, what's going to happen? One's going to get stronger and one's going to get weaker. So guess what happens? It's the same here as well. The electric field between two charged plates is a constant, as long as you're not near the edges. I'm going to repeat this one more time because Nick hasn't written it down yet. The electric field between two charged metal plates at all spots in between them is equal. Which is why the Milken oil drop experiment works in the first place, because you have a floating oil blob, it's not going to stay right in the center, right? It might move left or right, it might go down, it might go up. It doesn't matter because the electric field everywhere is the same. Whatever you dial it to. It's interesting. What am I dialing when I'm dialing? Putting electrons in the thing. Voltage would be convenient, wouldn't it? Well, here's an interesting thing also for parallel plates. If the electric field is the same, then the electric field is equal to force per unit charge. Agreed? And we just said energy is equal to voltage times charge. Agreed? Now notice energy is the U this time, not the E. So therefore, energy is the equal amount of work it takes to move it. Agreed? And that would be force times distance is equal to V times Q. If I move my Q over here, nope, I don't want to move Q. Yeah, I do. If I move my Q over here, I get F over Q times D equals V. If I move my D back over here, then I get something interesting. I get that the electric field between two charged plates is the voltage divided by the distance between two plates, which is something I can easily deal with, right? Put a 9-volt battery on there, two plates. I know the distance between them. I can find the electric field between those two plates.